This video will discuss what logic gates are, how they are created, and how they are used. Logic gates are the fundamental blocks of any digital system, just like our computers, cell phones, and other electronic devices. Basically, a logic gate has one or more input and only one output. So let's have a look on the first gate, which is called the AND gate. AND gate has this form. It has two inputs, the A and B, and one output. So let's assume that the input for A is 0 and for B is also 0. ANDing the inputs A and B will result to 0. Let's change the input for A. Let's say 0 and 1. ANDing A and B, this becomes 0. Similarly, if the input for A is 1 and B is 0, you will still get 0. The only time you will get 1 if both inputs A and B are 1, so you get the result 1. Observe that the result 1 can only be obtained if both inputs are 1. The next gate is the OR gate. OR gate has two inputs, A and B, and only one output. Let's assume that the input for our A is 0 and same with our B. So you will get 0. Let's try different input for A. Let's say 0 and for B is 1. Then that's the time you will get 1. As long as there are an input of 1, either in A or B, you will get 1. If both inputs are 1, then absolutely you will get a result of 1. So this tells us that the only time you will get 0 if both inputs are 0. But as long as there are 1 in the input, you will get a result of 1. So let's have a look on another gate. NOT gate has this form. It accepts one input and produces one output. And normally, whatever value you assign to A, you just negate the value. Let's say, for example, if you have an input of 0 for A, and then the result will become 1. If you have an input of 1, then the result is 0. So you are just inverting or negating the input. The next gate is the NAND gate. NAND gate has this form. It has two inputs, A and B, and produces one output. Observe the bar line at the top of A and B. So this indicates that the A and B has a negated result. So for us to see what is the meaning of negated result, let's assume that the input for our A is 0 and same with our B. We AND A and B, so we get result of 0. And then we negate this result, this will turn to 1. Let's have a different input for A, let's say 0, and for B is 1. We AND these inputs and then this results to 0. Then we negate the result, this becomes 1. Let's say for A is 1 and for B is 0. We AND A and B, this becomes 0. And then we negate that 0, this becomes 1. And lastly, if the input for A is 1 and B also is 1, then we get a result of 1. Then we negate this result, this becomes 0. So the next gate is the NOR gate. NOR gate has this form. It has two inputs, A and B, and produces one output. Let's assume that the first input for A is 0 and B is also 0. So we get a result of 0. And then we negate the A plus B, this becomes 1. Let's have another input for A. Let's try 0 and 1 for B. We add this result, A plus B, this becomes 1. And we negate this result, this becomes 0. Let's try 1 for A and 0 for B. We add this becomes 1, and then we negate, it becomes 0. Now let's try 1 for A and 1 for B. And as long as there is 1, the result will become 1. And we negate the result, this becomes 0. The next gate is surrogate, or also known as exclusively OR. It has two inputs, A and B, and produces one output. Let's assume that the input for A is 0 as well as for the B. Then it produces 0. The only time you will get 1 is when an input is 1 and the other input is 0. Let's say for A we have 0 and B is 1, then that's the time you will get a result of 1. Let's say for A is 1 and for B is 0, then that's the time you will get a result of 1. If both inputs are 1, let's say A is 1 and B is 1, then the result is 0. For surrogate, always remember that the only time you will get 1 if one of the input is 1. Otherwise, the result is 0. The next gate is the XNOR gate. XNOR gate has this form. It has also two inputs and one output. So let's say we have an input of 0 for A as well as for the B, and it produces 1. If we have 0 for A and 1 for B, then it produces 0. And similarly, if you have 1 for A and 0 for B, the result is still 0. And if both inputs are 1, then the result is 1. For XNOR gate, the only time you will get 1 if both inputs are similar. Both inputs are 0, you will get 1. Both inputs are 1, then you will get 1. Otherwise, you will get 0. Now let's try to draw the logic circuit for the given Boolean expression. For number 1, we have A plus B times C. Or we can read it as A or B and C. For number 2, we have A or B and C. And for number 3, A or B and A or C. So let's try to draw the logic circuit for each Boolean expression we have here. So let's try drawing the logic circuit for the first item. Let's start working with this side. So the operation for this is AND. So let's draw the AND gate. So let's write here the B and then the C. And then let's draw here another one. This time, let's work on this side. This is an OR gate. So OR gate looks like this one. And let's write here A. And of course, the output of this is A plus B and C. Okay, so that's how you draw the logic circuit for this Boolean expression. Okay, so let's try another one. So this time we have a parenthesis. So let's try working the innermost parenthesis. So we have A plus B. So let's draw the OR gate. So we have A and then we have B. And then we do the AND because this is an AND gate. Then let's write here the C. Okay, this is now the logic circuit for this Boolean expression. Okay, so let's try another one. So let's start with this. It is an OR gate, so let's write here the OR. We have A and then B and then they are connected with AND gate. So we have another OR here. So we have here the A and then we have here the C. So there you go. So this is now the logic circuit for this Boolean expression. So that's the end of this video, and thank you for watching.